How many times does this happen to you? You're going hiking with a friend, you're on a cliff and they're down in a valley. They get hungry and you realize that you're carrying all the foods. They say, hey, would you please throw me a donut? And sure enough, you have a donut. Donuts are fairly aerodynamic. We can ignore air resistance. You throw this one up in the air. It's a great toss, and your friend catches it without moving. Let's define the positive x and positive y directions here. And let's imagine that you're so practiced at throwing food that you know you threw that donut with an initial velocity of 6.40 meters per second at an angle 55 degrees above the horizontal. Furthermore, let's imagine that you somehow know that the donut's displacement in the y direction is negative 25 meters. Maybe you know the height of the cliff and you assume that you and your friend are about the same height. The things we don't know but want to calculate are the distance between you and your friend in the x direction, which will be the x displacement of the donut, and the amount of time it takes the donut from the time it leaves your hand to the time your friend catches it. Those are the two things we're going to try and calculate. This is a general projectile motion problem in 2 dimensions. They don't all involve donuts, but in my opinion the best ones do. The first step in solving a problem like this is just to organize our information. So I'm going to erase the pictures of you and your friend, and the cliff and the valley. Let's just put everything we know and don't know over on the left side. So we know the initial velocity and its angle, we know the y displacement, but we don't know the x displacement, and we don't know the amount of time it takes for the donut to go from your hand to your friend's hand. There are other things we know, though, that we should write down before we try solving this problem, otherwise we might not get anywhere. I would argue that once the donut has left your hand and before your friend catches it, we know the acceleration of the donut. Specifically, we know that the acceleration in the y direction is negative 9.8 meters per second squared because the donut is only under the influence of gravity while it's going through the air. The acceleration in the x direction is 0. We don't even need to write that explicitly. The donut should not be accelerating in the x direction. Gravity doesn't point in the x direction. In this case, it points down. We also know the equations of motion that will help us along the way. And there's one other piece of information that we can get pretty easily at the beginning before we try applying those equations of motion, and that is the decomposition of the velocity vector. What do I mean by that? Well, let me draw a triangle over here. We know that the velocity points up and to the right at an angle of 55 degrees above the horizontal, and we know that the initial velocity value is 6.40 meters per second. We can decompose that into a y component and an x component, and solve for those numerically, because we know the initial velocity and its angle. Let me show you. So looking at that triangle, we know that the sine of 55 degrees must be the ratio of the opposite side to the hypotenuse. That means that the sine of 55 degrees is the ratio of v0 y to v0. Well, we can easily solve for v0 y because we know the value of v0, right? It's 6.40 meters per second. So let's do that. v0 y is just 6.40 meters per second times the sine of 55 degrees. Put that into your calculator, and you should get out that v0 y is 5.243 meters per second. Now, that won't be the y velocity throughout the entire problem, but it is the initial y velocity. Let's write that over on the left, and we'll use it later. We keep a lot of significant figures here. The extra precision will help us in our calculations. So we write that down. Next, we can do the same for v0 x. This time it'll be the cosine of 55 degrees. It equals v0 x divided by v0. Solve for v0 x, and you get out 3.671 meters per second. We'll write that over on the left as well. Now that we've decomposed the initial velocity and written down the values, we can erase that triangle, and we can erase all the work on the right-hand side. Now let's apply the equations of motion to solve for either the x displacement or the time. I'm going to choose the time. Let's do that first. Now if we want to know the time, which equation should we use? Well, it has to be one of the top two. The bottom one doesn't have time in it. Looking at those two, one of them involves a final velocity, and we haven't written down any information about a final velocity. That means we're stuck with that middle equation. Now I'm going to write it over here on the right in terms of y instead of x. So the final y position should be the initial y position plus the initial y velocity times time plus 1/2 times the y acceleration times time squared. Okay, first let's just rearrange that to have the y displacement by subtracting y0 from both sides. So we do that. Now I'm actually going to bring the y displacement over to the right-hand side. That may seem strange, you'll see why in a minute. So that 0 equals negative delta y plus v0 y times t plus 1/2 ayt squared. Now I'm going to rearrange this equation in an even more suggestive fashion by setting it so that 0 equals some coefficient in parentheses times t squared plus another coefficient in parentheses times t plus a constant. Of course, the reason to do this is that we can now use the quadratic equation to solve for t. So let me label these three coefficients in parentheses, a, b, and c. And if you remember, the quadratic formula tells you that t equals negative b plus or minus the square root of b squared minus 4 times a times c, all of that under the square root, divided by 2a. When using the quadratic formula, it's very easy to choose the wrong coefficient or to miss a sign, so I encourage you to go back and make sure that I put all the coefficients into that expression properly. We can simplify things a little bit, going down to the next line, and now you're going to see that it's actually tough to tell whether we should choose the plus or minus solution until we actually put in numerical values, because we don't know what's negative or positive until we put in those numbers. So let's do that now. We put in our numbers for the initial y velocity, the acceleration in the y direction, the y displacement. We do all of that, and now we can simplify things even further. So now it's minus 5.243 plus or minus 22.748 meters per second, that whole quantity divided by negative 9.8 meters per second squared. Well, we encountered a similar problem in class. We want the time interval to be positive, so t should be a positive number. The only way that we'll get out a positive number in this case is if we choose the negative solution. If we chose the positive solution, we would have a positive number divided by a negative number. That would make t negative, and we don't want that. So we choose the negative solution. Sure enough, that gives us t equals minus 27.991 meters per second divided by negative 9.8 meters per second squared. That time comes out to be 2.856 seconds, which we can round off to 3 significant digits to 2.86 seconds. Okay, great. That tells us how long the donut was in the air. I'm going to write that time over on the left. So the last thing we need to do is figure out the x displacement. That's relatively easy once you've got the time. So we'll erase all this. Which of the 3 equations of motion should we use? So we need a displacement. That means we should choose the second or third equations of motion. But remember, ax is 0. There's no acceleration in the x direction. That means that the third equation of motion becomes trivial, right? It just tells us that the initial velocity equals the final velocity in the x direction. You can't really use that to calculate anything, so let's choose that second equation of motion again. And as you'll see, after we choose it, it becomes simplified because ax is 0, so that whole term goes away, and we just get that the displacement in the x direction equals v naught x times time. Well, we know the value of v naught x because we decompose the initial velocity. We know the value of the time because we already solved the equation of motion in the y direction, and of course time is a scalar. It's the same experience in the x and y direction. It doesn't have a direction itself. That means we can just plug in those two numbers. So delta x equals 3.671 meters per second times 2.856 seconds. That gives us 10.48 meters, or to 3 significant digits. The x displacement is 10.5 meters. We'll put that over on the left as well. So now we figured out the donut moved 10.5 meters in the x direction and was up in the air for 2.86 seconds. Aren't you happy that you finally solved a complicated projectile motion problem in 2 dimensions? Well, you're probably not as happy as your friend.